Hello and welcome to our new IONICON on-demand webinar. My name is Markus Müller and today I'm going to give an overview about the essentials of a proton transfer reaction mass spectrometer. Or in other words, why is a PTR not a PTR? Let me start this presentation with a few examples. This picture shows a small biomass burning plume in Georgia that I sampled on board the NASA P3 airborne laboratory. Such plumes consist of hundreds of compounds, many of them unknown. Therefore, I think it's very important to have a very clean instrumental response that does not generate artifacts. And here at IONICON, we try to solve this issue by our ultra-pure ionization. The second example is the controlled collision-induced dissociation of limonene in a PTR linear ion trap. Such controlled fragmentation can give a lot of insight into structure and composition. Sadly, COD does not only happen in a controlled way. Hard collisions at the extraction of the ions from the ion-molecule reaction can induce significant artifacts and even unwanted ion-molecule reactions. That's why IONICON-grade PTR-MS feature a soft ion extraction. The next example shows the chemical composition of organic aerosol measured by Ionikoron PTR-MS. Such a mass spectrum consists of more than 1000 chemical compositions. To get a quantitative response, it's very important for us that we understand the reaction kinetics. So, the third essential for an IONICON-grade PTR-MS is that we are able to easily calculate quantitative results. Now let's have a look at the last example. Here we see a picture of a field site where we measured eddy currents fluxes above grassland. In order to sample atmospheric turbulences without losses, the instrument needs a response time within 0.1 seconds. So the fourth essential is real-time response. Now let me summarize these four key parameters of an IONICON-grade PTR-MS. First of all, we need an ultra-pure ionization process to produce our analyte ions. Then we have to extract the ions from the reaction cell without affecting them. In addition, we need to be able to quantify our time traces even without direct calibrations. And, of course, we want to have it in real time. Now I want to start to give some insights into our ultra-pure ionization technique. An ultra-pure ionization is extremely important for us. Hardly any scientist or commercial customer will only focus on a system with only a few VOCs. Most of us face complex mixtures with several hundreds of compounds in it, like in this small biomass burning plume. And of course, if you sample such complex mixtures, artifacts caused by dirty and inhomogeneous ionization will significantly mess up the data interpretation. So, what is IONICON doing to prevent such artifacts? Let's have a look at this schematic illustration of our current PTR-MS technology. A PTR-TOF 6000X2 features a hollow cathode ion source, the drift tube ion molecule reaction cell, an ion funnel to boost the ion sensitivity, and a hexapol ion guide to efficiently extract the ions into the TOF-MS. What drives our technology is the simple reaction H0 plus VOC results in a protonated VOC plus water. So we already see that we demand for a pure primary ion signal. We generate this pure primary ion signal in two steps. Step 1 is the water plasma discharge, where we generate all ionic fragments of water. The second and more important step is a recombination chamber, where the produced ionic fragments almost completely react forward to pure H0+. At the same time, the neutrals of this reaction chamber are efficiently pumped away. In the case of a water plasma, these neutrals are mostly water, but when we have a look at the recombination chamber reactions, also consists of radicals like OH. In my opinion, the most important advantage of this well-established and robust ion source design is the complete separation of the primary ion production from the ion molecule reaction chamber. Now let's have a look forward towards the drift tube reaction cell where the primary ions and the sample air are injected. On the right, I have added a schematic visualization of parameters starting from the ion source towards the ion extraction into the TOF MS. Very importantly, we have designed our ultra-pure ionization chamber to have very homogeneous reaction conditions. Our applied DC fields, controlled pressures and temperatures, together with finely tuned extraction energies, result in a constant electric field over number density ratio throughout the whole reaction chamber. And exactly this constant E/N ratio allows for a controlled and homogeneous ion molecule reaction. At the same time, parasitic ions like O2+ are already significantly reduced in our recombination chamber, and neutrals or radicals from the plasma discharge can't reach and transform our sample. These are some schematic visualizations, but now let's have a look at some real data. On the top, I've plotted the ratio of protonated xylene to the charge transfer product of xylene with parasitic O2+. We only see around 1% of the charge transfer product, and because the primary ion production is completely separated from the ion molecule vector, this ratio is completely independent of the electric field strength. The bottom panel displays fragmentation of xylene. Many of you will now think, what? Fragmentation of xylene? But xylene is a very robust aromatic molecule. There is no fragmentation of xylene. And indeed, for an IONICON-grade PTR-MS, we don't really see fragmentation of xylene. A potential fragment on mass over charge 91 is, dependent on E/N, always below 1%. But please see that as an upper boundary, as I have extracted the data from a calibration gas experiment with around a dozen of compounds in the sample. So a fraction of this low mass over charge 91 signal can actually be caused by an impurity of an interfering ion. Now let's have a look at how a not so ultra-pure ionization can look like. Therefore, I have schematized the ionization process of a different CIMS that is also called PTR MS by its manufacturer. They use an off-axis ion source that is operated with up to 30 SCCM of water vapor. The plasma afterglow products are directly injected into their focusing RF reaction chamber without any physical removal of any neutrals or parasitic ions. Again, let's have a look at the conditions in the axial distance towards the extractions into the mass spectrometer. First of all, ionization in an RF reaction chamber leads to pretty undefined reaction conditions. Secondly, parasitic ions like O2+ will have a significant concentration in the plasma afterglow regions, but will drop throughout the reaction cell due to the reactions with the high neutral water concentration. This is a very similar process that actually occurs in IONICON's recombination chamber. This means, although only little O2+ might be actually measured, UCs will anyway undergo parasitic charge transfer reactions in the reaction chamber. To illustrate this, I have prepared two schematics for the other CIMS technique and an IONICON PTR-MS. Where we see only around 1% of charge transfer products, the other technology has significantly more. And of course, in case of an unknown and complex mixture that most of us analyze, this significant side reaction will cause several artifacts, and a proper assignment of compounds will not be possible and will be very difficult. Another key advantage of the IONICON solution is the soft ionization at homogeneous reaction conditions. So let's go back to the xylene example. While a PTR TOF 6000X2 does not really see this fragment, the other CIMS sees up to 10%. This means the RF reaction chamber adds a significant amount of energy to the applied electric drift field. We see that other CIMS fragmentation is very much dependent on the applied RF amplitude. So in principle, the other CIMS can easily reduce the fragmentation by just reducing the amplitude, can it? But here comes another issue. While IONICON's DC drift tube reactor has very homogeneous reaction conditions, what results in pretty stable sensitivities throughout a broad range of E/n, the RF design is much more limited. Good sensitivities can only be reached at a very narrow DC and RF voltage range. With an applied E/n of around 150,000 plus the more or less undefined influence from the RF field, reaction conditions are significantly harder than typically operation conditions of an IONICON PTR-MS. The clearest influence is visible for the benzene signal. Benzene only reacts with H3+ but not the water clusters. Therefore, the other CIMS needs high electric fields to break up the water clusters that are in equilibrium with the high absolute humidity in the reaction chamber of up to 25%. A PTR-MS, on the other hand, only reflects the humidity of the sample in the drift tube reaction cell. That is typically in the range from 0 to 2% for breath gas analysis. And if you look at the benzene response above, even at extremely soft reaction conditions of only 60,000, the PTR-MS has around 30% of H3+ primary ions left that react with benzene. Others, like acetone, that react with water clusters with a similar reaction rate will not be affected. Nevertheless, at normal operation conditions of around 120 to 130,000, the effect of sample humidity on sensitivity is insignificant. Now you guys probably start to think he's talking about acetone and aromatic species. These compounds are actually super easy to measure. We are more interested in real compounds. And, of course, these real compounds tend to fragment even at the very soft conditions of an IONICON PTR-MS. As an example, I've plotted some ions from pannonic acid. Pannonic acid is a semi-volatile oxidation product from alpha-pinene, and as you see, has an acid and a ketone group attached. Such compounds with multifunctional groups easily fragment, and therefore a reduced E/n significantly reduces fragmentation. As an example, I have plotted the E/n dependencies for the protonated parent molecules plus a low E/n fragment and a high E/n fragment. As we can see, we have to reduce the electric fields down to 60,000 to measure a dominant parent molecule peak. Now, to make my point, let's add the transmission efficiency of that other CIMS to the y-axis. Again, this does not account for additional E/n induced from the applied RF field. But even if we ignore the influence of the RF, the very low transmission efficiencies towards soft ionization settings will make sampling of a dominant parent molecule impossible. Now let me summarize the first essential of an IONICON-grade PTR-MS. We achieve our ultra-pure ionization by little impurities of parasitic ions and radicals in the reaction chamber. We reflect the conditions of the sample in the reaction chamber. An IONICON PTR-MS has fully controllable reaction conditions, including pressures and temperatures. We have stable sensitivities over a large E/n range. The user can choose between softer and a harder measurement, or simply automate between different settings, and IONICON's ion source design allows for a clean SRI option for the ionization with NO, oxygen, krypton, and xenon plus. The second essential is the soft ion extraction into the mass spectrometer. Undefined or high electric field strength at the extraction region might induce artifacts due to collision-induced dissociation or even unwanted ion molecule reactions. So let's have a look at the ions in our drift tube reactor. Within the 100 microseconds of residence time, the ions will slowly diverge towards the end of the drift tube reactor. To increase sensitivities, a few years ago, IONICON has introduced the ion booster that efficiently funnels the ions. To illustrate the performance of the funnel, we have prepared a short clip. Head space of alpha-pinene is extracted and injected into a Teflon bag and sampled by PTR MS. Without the activated funnel, we measure around 1400 counts at mass over charge 137 and around 1000 counts at the fragment on mass over charge 81. Now we activate the funnel and the sensitivity is immediately boosted by a factor 25 without affecting the fragmentation pattern. This means IONICON's ion-booster technology does not alter the reaction conditions nor induce fragmentation. This figure, extracted from their respective patent application, compares the fragmentation patterns of octanol with and without funnel for various E/N settings. The results are very comparable. The second step for a soft and efficient ion extraction from the drift tube reaction chamber is our hexapol ion guide. The hexapol guides the ions into the ultra-high vacuum of the TOF-MS, while the residual sample gas can efficiently pump away. The advantages of a hexapol ion guide compared to a quadrupole ion guide that other manufacturers use are the typically lower confining energies needed and the broader mass over charge range that can be efficiently transmitted. So to summarize, if we look again at the axial distance from the drift tube towards the TOF-MS, all values stay nearly unaffected. E/N is stable, O2+ is stable, and even the fragmentation stays stable. Therefore, we also see no induced and unwanted collision-induced dissociation or ion-molecule reactions. So what is the difference to other technologies? Proper coupling of a reaction chamber to a TOF-MS is difficult and requires a lot of experience in ion-molecule reactions. Inhomogeneous reaction and extraction conditions will easily result in an increased fragmentation and unwanted hard ion molecule reactions. In addition, the quadrupole ion guide, which is used by others, will only transmit a reduced mass over charge range. Therefore, the operator has to choose and select the mass over charge range of interest. For IONICON's hexapol solution, the transmission function is much smoother. Therefore, there is no need to pre-select a mass over charge range of interest. Now let me summarize the second essential of IONICON-grade PTR-MS. Soft ion extraction is ensured by the ion funnel that does not affect the reaction conditions and energies, and the hexapol ion guide that transmits a broad range of mass over charge. Therefore, we only add a little degree of additional fragmentation due to the extraction into the TOF-MS, and we can reflect the conditions of the reaction chamber by the TOF-MS detector. Now we have extracted the ions from the reaction chamber and detected them with the TOF-MS. So the next essential step is to quantify the time series. To illustrate the importance, I want to show you a Caron PTR-TOF-MS condensed organic mass spectrum that contains more than 1000 chemical compositions per spectrum. Of course, we can only calibrate for a small fraction of these compounds. So we are dependent on a reliable ion chemistry so that we can quantify the results simply based on reaction rates. And one of the important steps towards quantification is the characterization of the instrumental response. So we add a calibration gas standard and calculate the relative mass discrimination by division with the expected collision rates of the compounds. This normally results in a nice and smooth figure as plotted here. The slow increase for smaller masses is caused by the hexapol interface, the near constant plateau by the TOF-MS. To illustrate the advantage of the hexapol, I have also added an example for a quadrupole interface that shows a much more distinct cut towards lower mass over charges. Now let me add some more compounds from the calibration gas standard to double-check the instrumental response function. These additional points clearly agree to the calculated instrumental response function. To illustrate the accuracy, let's have a look between the differences of the calculated and the measured sensitivities. And all ions perfectly agree within the 5% accuracy of the applied calibration gas standard. Only the acetaldehyde concentration in the standard seems to be a little higher than declared. But this predictable instrumental response function is not only limited to the VOC range. As we could show in a recent analytical chemistry publication, this is also true for a much wider volatility range. So even semi or low volatile organic compounds can be efficiently be quantified simply based on reaction rate constants. Now let's compare the other CIMS with our PTR-MS on the right side. To simplify the results, compounds that might show fragmentation in the PTR-MS are not added, for example isoprene. This time I have also added NOAA's H3+ top CIMS to the mass discrimination plots that uses an IONICON designed reaction chamber coupled to a non-IONICON TOF-MS, very comparable to the other CIMS. NOAA's H3+ CIMS shows a pretty stable response, with only benzene a little bit lower. The other CIMS, on the other hand, show significant differences even between similar compounds like the two ketones acetone and methylethyl ketone, or xylene and TMB. These clear variations cannot be explained by the reaction rate constants nor the instrumental response function. A solid quantification of unknown compounds is therefore not possible. To summarize the third essential, for good quantitative results of uncalibrated compounds, we need a predictable and stable instrumental response function, and the ion molecule reactions have to occur with collisional rate. Then we get good quantitative results from the VOC to low volatile organic compound range. That brings us to the last essential, the real-time response. Many applications demand for a real-time response. We have already seen the airborne and the eddy coherence flux examples at the very beginning. Another example is breath gas analysis, where the alveolar fraction of the sample has to be measured in really high time resolution. And to illustrate the quick response of a PTR TOF-MS 6000X2, let me show you the following clip. So we prepared a solution containing heptanone, decanone and tridecanone for injection with our liquid calibration unit. The volatilities of these ketones range from VOCs to IVOCs. The volume mixing ratios of each ketone are around 30 ppb. So we have a very stable concentration, and once we disconnect the liquid calibration unit from the PTR-MS inlet system, we see a very rapid decrease of all signals. This was measured at a PTR temperature of 100 degrees. Now let's have a quick look on how the response for these three compounds look at 60 degrees. I have also added the 1/E and 1/E squared lines to the plot. Heptanone and decanone show an immediate decay. The tridecanone decay is slightly delayed. Let me plot the time response versus the volatility of each ketone. Heptanone is now on the far right, tridecanone on the left. I have plotted the response times for three different typical operation temperatures of a PTR-MS ranging from 60 degrees to 100 degrees. Whereas the VOCs heptanone and decanone show no significant difference in terms of 1/E squared decay, the tridecanone response decreases from 2 seconds to 0.8 seconds with increasing temperatures. Now let me add the data for the other CIMS to the plot. Whereas the VOCs show a very similar response, the tridecanone response of the PTR TOF 6000X2 is at least a factor 10 quicker. And with the Caron particle inlet that is exclusively available for IONICON PTR TOF-MS, we can even extend the real-time response from VOCs and IVOCs to SVOCs and LVOCs. Finally, we have all the 4 essentials of an IONICON-grade PTR-MS explained. I think we all agree that pure ionization soft ion extraction, quantitative results, and real-time response are absolutely necessary, and these are only provided by IONICON, home of PTR MS with more than 350 PTR MS sold. And with that, I and the whole IONICON team want to thank you for watching. If you have any further questions, please don't hesitate to contact us.
Thank you very much for watching this IONICON webinar. As you are already sitting in front of your computer, take the opportunity and visit ionicon.com. On this website you will find many useful information about PTR MS. For example, you can have a look at our current product portfolio and see the specifications of all our instruments. Maybe you're interested in your own personal showcase or just want to read about the analytical service we can provide. Our PTR MS publication database covers publications from various expert groups from all over the world. If you have any further questions, please do not hesitate to use the contact form or contact us in any other way you would like. So please go ahead and surf to ionicon.com.